Hello everybody. Today we're going to be taking a look at the LabFlow experiment entitled Energy and Specific Heat. This is a thermodynamics experiment that really very closely mimics some of the labs that we would do in person in the lab. Key learning objectives here are to get used to the energy terms that are used commonly in chemistry, the calorie and kilocalorie, as well as the nutritional calorie, and how those compare with the other very popular unit of energy called a joule. We're also going to be doing some specific heat calculations. And so there are basically two types of experiments we're going to be doing in this lab, but both of them rely on this same sort of an equation as listed here in the handout. So this one is written a little bit different to what you might find in a textbook, in which case in the textbook, this is usually written as the heat Q equals mc delta T. So the same pieces as are listed down here, m being the mass of the material, capital C is the pretty universal variable used for specific heat, and T is a change in temperature. It's worth noting that anytime you see a delta in chemistry, a change, it's always final minus initial. So if something is getting hotter, the final temperature is higher, that delta T will be a positive value. If something is getting colder over the course of the experiment, that final temperature would be lower than the initial temperature, and so delta T would be negative. It's an important thing to pay attention to the signs in a thermodynamics or thermochemistry experiment, just so that you don't get mixed up. Things that are releasing energy end up having a negative heat value, a negative Q. Things that are gaining energy have a positive heat value. All right, so heat is just the amount of energy that something is gaining or losing in the course of the experiment. Specific heat, labeled with C, notice the units here are energy per the amount of material and per the amount of temperature change. Specific heat is a measure of how much energy it takes in order to cause a change in temperature of something. And so that's described as we go through the handout here. Sorry about that. There we go. So they do give us some specific heats here in the table. Calories and joules are just two different units. Notice the grams and degrees Celsius on the bottom of these units are the same. So we're just changing the energy unit. And you can see this relationship then that there are 4.18 joules for every calorie. That's just a conversion factor you can use back and forth. Hopefully you can also see from the numbers that are given to us that liquid water, has a remarkably high specific heat. That is, water can absorb a large amount of energy before its temperature changes. And that's why in industrial machines we use water to cool things. There's probably water running through the radiator on a car that you might drive because it can cool down the metal of the engine very efficiently. People have been using water to cool metal down for a long time because it has a much higher specific heat than does the typical kind of metal that you might be cooling down with that water. So as they mentioned down here, there are two parts to this experiment. In the first part, we're going to be using a calorimeter, in this case an open cup or coffee cup calorimeter, to determine the specific heat of a metal. And from that specific heat, we can identify it using this table. Okay. So we'll talk about that in a moment. In the second part of the experiment, we'll be looking at the nutritional side of things, burning food samples to determine how much energy was present. In this case, we're using the capital C, the dietary calorie, which is equal to 1 kilocalorie in scientific units. So as we go down and we look at this, part one, as it's written here, is this styrofoam cup calorimeter. And basically what we're doing is the old, blacksmith style experiment where we're going to be taking a hot piece of metal that we know its size, its mass, and we're going to be putting it into water. And what's going to be happening when we do that is the same thing that's happened for blacksmiths for, forever and ever since humans started doing this, is that the heat will come out of the metal into the water, and the temperature will go up. The temperature of the water, that is, will go up. So the important part that's not exactly shown on this diagram is the fact that a calorimeter is insulated. And so in using a styrofoam cup, or sometimes two nested styrofoam cups, we are insulating this. Any calorimeter will have this insulation around it because one of the key relationships that we're going to be taking on here as we do this is to say that the heat gained by the water is equal to the heat lost by the metal. In order for that to be true, we can't lose or gain any heat from the environment. And so we have to have a perfectly insulated container. If you notice the wording that I used here, I said the heat gained by the water, so that's going to be a positive number, is going to be equal to the heat lost by the metal. Losing energy is going to be a negative. These two numbers will have the same numeric value, but opposite signs to indicate their the direction of heat transfer. And that is the metal is losing energy, so it has this negative sign here. Its final temperature will be lower than its initial temperature, right? It'll start off really hot on the thermometer, and it will cool down to some intermediate temperature. Conversely, the water would have started pretty cold, relatively cold, and it will go up in temperature until it's at the same final temperature as the metal. Right? That's another key thing here. The final temperature will be the same. These two materials will come into thermal equilibrium. And so when we go through the data later on, we will know the mass and the specific heat for water. And so that experiment, remember, Q equals mc, this is all of water over here, and the change in temperature for water is equal to, I like to circle my negative signs so I don't lose them. That's just something I grew up doing. mc for the metal, delta T. So if we know the mass of the water, and we know its specific heat, and we know the two temperatures that go into this for the water, its initial temperature and the final temperature of the system. For the metal, we will know its mass, and we will know its two temperatures, and so we can figure out the specific heat. Okay, so that's kind of a rundown of what the math will look like, and we'll look at the report in just a moment. When we get into the calculations, you'll see this, and I'll run through that in our example in a moment. The other example here is energy of food. And so for this setup, we'll be just calculating the calories in a sample. And some numbers that you may already know, or you could pretty easily put into your brain here is that fat is more energy dense, providing 9 dietary calories, or 9,000 scientific calories per gram, whereas carbohydrates and protein are somewhat less energy dense. They provide about 4 calories per gram. And so if you look at your nutrition label on any old product that you find in your kitchen, you'll see a gram measure for total fat, for carbohydrates, and for protein. If you multiply those gram numbers by 9 calories per gram for fat, or 4 calories per gram for carbs and protein, you should come out reasonably close to the calorie count on your nutrition label. It won't be perfect because of labeling laws. There's some rounding that's allowed, and so you will probably not get a perfect answer out of that, but you'll come close. So as we get into the lab itself, of course, we're going to click on the report and choose virtual data here off to the side. And so, it goes through and it tells us the steps of the procedure: obtain a hot plate and a beaker and do all of this stuff. Obtain an unknown metal and record its identification number. Here is the identification number. I've been assigned unknown number 3 in my example. So I'm just going to put a 3 in that box. Okay, the mass of the unknown metal, I wish I could skip the data collection part here, but there's not that much of it. Here's the empty cup, 1.727 grams. Again, with a digital balance, we'll just read what's displayed for us. The filled cup, 46.187. Notice the procedural step says up here, add enough water to the calorimeter so that the metal will be completely submerged, approximately 50 to 100 milliliters, but then measure the mass. If you sort of in your head subtract these, you can see that's about 45 or so grams of water. So it wasn't 50 to 100, but it was apparently enough that it was submerged. A lot of procedures will read that way. They'll say approximately some amount, but then measure the particulars, measure your specific numbers. So here's 46.187 from the balance. Then I go on temperature. Remember analog scales, we want to infer one extra digit. And so this one is marked at 90, I think I would call that 99 exactly, which I'll represent as 99.0, right? I can read it to the ones place. I want to estimate one more digit. And initial temperature of the water, let's call that 23.9. Again, if your estimate is a little different to mine, that's okay. Your calculations will be based on your numbers. Final temperature of the water, I'll call that 24.9. Now, I do want to point out something about this kind of experiment. What was the final temperature going to be? Well, it has to be between the two starting temperatures, right? When we dunk this hot piece of metal into the cold water in the calorimeter, that metal starts at 99 degrees and it's going to start decreasing in temperature. The water in the calorimeter started at 23.9. It's going to start increasing in temperature. And so the final temperature had better be somewhere in the middle. In most cases, probably pretty close to the water, again, because water has such a high specific heat. So if you were calculating a final temperature, which you may do in some homework questions or something like that, your answer here for final temperature had better be between your two starting temperatures. And if not, you've done something wrong. So we'll go ahead and forward, fill out a few more things. So this is a second trial that we're going to be doing. 46063, 90, maybe that's 98.9 this time. And I'm trying to go through this relatively quickly so that you can see the calculations. All right, so we've got all of that. And then the calories per food. So what food is being analyzed? They say your food sample is Doritos chips. In the lab, we used to do this with peanuts. Peanuts burn really well, but of course, a number of people are allergic to peanuts. And so we have switched to Fritos corn chips, which burn really well as well. They get kind of drippy, but that's okay. By the way, this kind of analysis, although in the picture we're using a soda can, an aluminum pop can, it makes a really good calorimeter. The bottom of a can like this is concave, and so whatever heat happens when you're burning the food underneath of it, a lot of that energy does actually get filtered or funneled up by that concave shape into the water inside the can. So even though it seems a little bit, maybe cheap or gimmicky to use a pop can for this, it is actually a really good vessel to do it. It'd be better if it was more insulated on the sides and things, but this one you can see kind of does have a little sleeve on it or something. All right, so again, we're measuring our temperatures. Again, the temperature of the water goes up as it's being heated by the energy released from the food that's going to burn underneath. With most foods, the material doesn't burn completely, so here's the little charred bit of chip that's left over. And ultimately, we'll want to know how much food actually burned, because that's the amount of the mass that released the energy. So we'll end up subtracting this amount of ash later on. Okay, and here's a nutrition label that they picked from something. Serving size, those are going to be up at the top here, 55 grams. Okay, again, you can see the numbers on here, total fat, saturated, and trans fat as subcategories. Cholesterol and sodium we're not talking about today. We've got total carbohydrates there and protein. All right, so total calories per serving up at the top, 230. Great big letters so that we can find them. The fat in one serving, total fat right there is 8 grams. Carbohydrates in one serving, total carbs, 37 grams right there. The difference here between total carbs and sugars, fiber, all of that is biologically important, but from a chemical standpoint, fiber and sugar have the same energy density. So biologically, our guts don't break down fiber, and so it's treated differently. But from an energy delivery standpoint, we're going to be looking at that total carbs number because we're burning it, and it will all burn. Protein in one serving, it looks like that says 3 grams. Okay, so we've got that. And that's the end of the data collection. So we'll go ahead now and showing me my data here. Here's my data in a nice little table. And we go on down a bit. Now, here's the first place I'm going to start doing some math. Now, remember that for specific heat, my equation that I'm going to be using all the time is that, and I'll put it over at the side over here, Q equals mass times specific heat times change in temperature. And so when I start looking here, mass of the water, of course, now I'll take my calorimeter with water in it and subtract the empty calorimeter. And so I get my numbers there. Pull up a little calculator off to the side. Throw that over there. I'm not going to do both trials anyway. You will. I'm not. So 46.187 minus the empty cup was 1727. And so I get 44.46 grams. Okay. Temperature change. Now here's where you have to be real careful about your signs. Notice that LabFlow says do not include a negative sign. Okay? So all that stuff I said about being careful with your signs, that's important. But for simplicity's sake, they've asked us not to use any negative signs for this particular lab experience. So the temperature change of water. Temperature change of water, temperature change of anything is always final temperature minus initial. So the final temperature is here, 24.9 degrees Celsius, and the initial temperature of the water was 23.9. Now that I look at the numbers, I probably didn't need my calculator for that, but it's here. So 1 on my calculator, but I should write 1.0, right? Significant figures are important. And the significant figures rule for subtraction says that I use the same number of decimal places as the number with the fewest decimal places. So these both have one decimal point, one decimal place in them. Even though my calculator just said the number 1, I'm going to add in that 1 decimal place. All right, now here's the heat gained by water. Let me go up here and get my pen back. The heat gained by water now, it's that Q equals MC delta T. Q is heat equals the mass of the water I just calculated at 44.46 grams. Right, that's that number. Specific heat of water. Well, I need to get that out of the PDF. They do want it in the calories energy unit. So when I look at the PDF for water, I see that, in fact, the unit of calories is defined by this. It takes 1 calorie of energy to raise 1 gram of water's temperature by 1 degree Celsius. So my value is 1 there. And my temperature change is 1 degree Celsius. All right, now if I look at my units for unit cancellation purposes, my grams are going to cancel right there. My degrees are going to cancel right there, and I'm going to be left with an energy unit here in calories, and that's what I wanted. And so if I pull back up my calculator, I'll say I've got 44.46 times 1 times 1. Oh gosh, didn't need the calculator again for that one. So 44.46 calories of energy were absorbed by the water. So if we were outside of LabFlow, this value would be a plus 44.46 calories. that means that the metal lost 44.46 calories. Again, if the problem asked us just for the heat for the metal, we would say negative 44.46 because it lost that energy. The temperature went down. But they say do not include a negative sign. And in fact, the wording here is carefully laid out. So they said heat gained by water, well, it's 44 calories. The heat lost by the metal is also 44 calories. And sort of the sign is taken up by those words. Gained is a positive, lost is a negative. Okay, but the number is the same. That, again, depends on the fact that our calorimeter didn't leak any energy, right? So it was well insulated. It's an assumption that we're making, but it's the best we've got. Okay. Now when we go back to our, there we go. When we go back to our metal now, our temperature change of the metal, let's go back to the right color there. Okay, temperature change of the metal, we're going to say the same equation, Q equals mc delta T, but now we're talking about the metal. And, oh, sorry, I'm jumping ahead of myself. We'll get back to that. Temperature change of the metal I could have done with simple subtraction. So up here is my final temperature, 24.9, minus my starting temperature, or subtracted from my starting temperature, was 99 degrees. So be careful again with the language here. Final temperature always comes first. So the metal ended up at 24.9 degrees. It started at 99.0. I don't know why there's 3 zeros there, but the difference is 74.1. The temperature change was a negative 74.1 degrees because it got colder. It went down. But again, LabFlow tells me do not include a negative sign. So we'll ignore that. We'll just say 74.1 degrees. All right. Now, where I was headed when I got ahead of myself here. For the specific heat of the metal in calories per gram degree Celsius, we're going to use the same equation, but we're solving for C for the metal now. So if you're an arithmetic person, you can plug in the Q value that you had for the metal right there, Q. You can plug in the mass of the metal, which we had up here somewhere, right, 20.885 from M. And you can plug in temperature change right there. Okay. If you're an algebra person, this can be rearranged and to show C equals Q divided by M delta T. Either way you want to do it, you'll get the same answer. I'm doing it this way so I can show you the units. So 44.46 calories per 20.885 grams. And temperature change 74.1 degrees C. All right. And so again, let's pull up my handy little calculator right over here. 44.46 divided by 20.885 divided by 74.1. I get that disaster of a number, 0.0287, etc., etc. I do want to round for significant figures. So if I look at this, my least significant number, fewest number of significant digits, was my temperature with only 3 significant digits. And so I'm going to round this number to 3 significant digits. Remember, leading zeros never count. So 0.0287, and that 7 is going to stand because the next number is small. So 0.0287, right? 0.0287. All right. Specific heat of metal in joules. Well, all right. I just need to convert it. Remember that conversion factor that we saw where we said 1 calorie is equal to 4.184 joules. And that's in the reading. It's also embedded in that table that we looked at of specific heats. And so if I have this number over here, 0.0287 calories per gram degree C, and I want to convert that, I can say, well, I want calories to go away. I want joules to show up. So 4.184 joules per calorie. And those will cancel like that. And so when I go and I look, again with the calculator, I have to move a little. I have this long number, so 0.0287 times 4.184 gives me 0.12. Again, it's going to be three significant figures, so 0.120. 0.120. I only changed my energy unit, joules, right? The gram and the degree C didn't change. So right there at the bottom, my last answer would be 0.120. Okay. So the average specific heat, you would have done this twice, two different samples. You're going to average these two numbers together. Notice the units here, they want you to use the joules unit. So you're going to use the very bottommost numbers in your table and average those guys together. And then identify the metal based on the average specific heat. So we got a joules number of 0.120. When we go back here into the PDF and we look, and we say the joules number is 0.120, looks like probably lead in my case. It's the only number that's reasonably close. Okay. So there's a little bit of experimental error, but amongst those four that they gave me, iron, copper, aluminum, and lead, it's going to be pretty easy to see that it's lead in this case. Okay, and so I'll pick that from the list. There are tables and tables and tables of specific heats of metals on engineering databases and things like that. And what you're going to find is that most of your metals are going to have, or the so-called industrially useful metals, are going to have specific heats kind of around the 0.3, 0.4, 0.5 kind of range on this joules per gram degree Celsius scale. Aluminum has a particularly high specific heat. That is, it absorbs a lot of energy before it changes temperature. So you've got aluminum there at 0.92. You've got a few metals that are going to be different. So lead is the one example here. There are dozens of metals out there and even more alloys. So you could really get bogged down in a table if you wanted to. But this table is going to do it for you. Okay, that's all you need for the lab. All right, when we go down and we look at the calculation of food samples, this is the canned stuff that we talked about. This is the same kind of idea, except that what we had, let me see if there's a decent diagram here to save me having to draw one for you. That's much better than what I would draw. So this is the setup. You'd have the food sample sort of suspended underneath the parabolic bottom of this can. The can's got water in it. You've measured the temperature of the water to begin with and the mass of the food sample. You set it on fire. You let the food sample burn until it stops burning. Measure the increase in temperature in the water and then see how much of the food actually burned. And so what we want to know is how much energy came out of that food. Ultimately, to calculate down here, it's energy density, calories per gram of food. Okay, and notice it's kcals, which is a kilocalorie in scientific calories. That's equal to 1 dietary calorie. So same kind of deal here, except the only thermodynamic entity we have is the water. So let me pull up my calculator again, put that maybe in the middle for right now. No, I don't like it in the middle. Put it over here. So they want us to calculate the mass of water. So again, we'll just subtract the can with the water in it. We'll subtract away the empty can. So 119,499 minus 12.606. Again, 3 decimal places. So 106,893 is going to be my answer. All right, temperature change of the water. Again, I've got initial and final temperatures here. I'm not going to use my calculator for that. I know it's 1.5 degrees. It's a positive. They tell me to make sure it's a positive, but it's a positive anyway. It went up. So the heat gained by water, well, what's our heat equation? It's the same thing we used up above. And so heat gained by the water, Q equals mc delta T. All right, they want it in calories. So mass was 106,893 in grams. My specific heat of water, again from the PDF, was 1 calorie per gram degree Celsius. And my change in temperature was 1.5 degrees C. Okay, again, notice my units are going to cancel. Grams are going to give way there. Celsius degrees is going to give way there. I'll be left with calories. So again, back to the old calculator here. I'm going to say that 106,893 times 1 and then times 1.5. Again, I'll round it. Looks like my temperature in this case is my limiting factor. So 1.5 degrees is my limiting factor. Two significant figures. There we go. And so 160 is going to be my number. Remember, without a decimal place, that trailing 0 doesn't count. So 160 is, in fact, two significant figures. Now, I am going to keep that longer number because I don't want to round anything in intermediate calculations. So I'm going to write this down, and I'm going to hang on to it, but I'm going to report the rounded number over here because I don't want to get marked down for the wrong number of significant figures. Okay. Next, heat gained by the water. Well, it's the same thing, but notice the unit changed. So if I had 160 calories, that's going to be 0.160 kcals, right? There's 1,000 calories per kilocalorie. Heat lost by the food. Well, that's all this heat, right? Again, I'm assuming that the water only warmed up because I was burning the piece of food underneath of it. So these numbers are going to be exactly the same as what I had up above, calories and kcals. Again, by way of units, if I wanted to do this in a totally standalone thermodynamics thing, I would say the water numbers would be positives because it's absorbing energy, it's getting hotter, and the food numbers would be negatives because it's releasing energy, it's losing energy. But in LabFlow, they tell me do not include a negative sign. What's the mass of food burned? Well, the initial mass and final mass are both measured for me right up here. And so I can subtract those. I started with 1.871 grams. I set it on fire. I let it burn out. And there was 0.750 grams of ash left over. So 1.121. That's the amount of food that actually burned, that actually broke down and liberated its energy. And so this last step, I can look at the units and see what's going on. I want the calories per gram of food. This is sometimes called the energy density of the food. And notice the units they want, kcals divided by grams. Well, here's the amount of energy in kcals. And here's the amount of food that released that energy. And notice when I do the math on that, my answer is going to have units of kcals per gram. So 0.160 divided by 1.121 gives me this long number. And again, I'm going to round it, okay? So I want 3 significant figures based on my energy. That's going to give me 0.143. Okay. Now, I did mention significant figures earlier and why I wanted to write down this whole big number up here. Notice that if I had used that whole big number, kcals divided by 1.121 grams, now notice that my limiting significant figures number is going to be the mass. So it's going to give me 4 significant figures, as opposed to the 3 I was forced to use here. So 4 significant figures that I could have reported 0.1427. had I used that longer number. Now, does that extra bit changing from a 2.7 to a 3, does that make any difference? I don't know. Sometimes it might, but in this case, you're going to be rounding to 3 significant figures for all of this, and so we would have ended up rounding it anyway. Okay, so don't stress about it, but this is how you should be filling it out for LabFlow's sake. All right, so that's the deal there. Is that a big deal? 0.143 dietary calories per gram. I don't know. Probably not too bad, right? If we wanted to make that a more reasonable serving size, we could convert it up to ounces. An ounce is 28 grams. So if I take this number times 28, that's 4 calories per ounce. That doesn't seem tremendously bad. In fact, it seems vanishingly low. So hopefully I haven't done my math wrong as we go through this, but that's what we've got, okay? So mass of the water, temperature change, heat gained by the water, kilocalories. I think we're all good. I think everything's okay here. So that's the idea of how you want to go through this, okay? Lastly, we're going to be talking about that nutrition label analysis, and these numbers came from my nutrition label when I read it. So I said there was 8 grams per serving of fat, 37 carbs, 3 proteins. And remember those conversion factors. It was 9 dietary calories here, capital C calories or kcals, 9 calories per gram of fat. So I've got 8 times 9 is 72. For carbohydrates and for proteins, the number was 4. And so I've got, is that right? 148? Gosh, I'm second guessing myself. 37 times 4. Yeah, 148 grams there, calories there for carbs, and 3 times 4 is 12. So that's using those energy densities I talked about. So I guess I can write those down right here. Times 9 capital C calories per gram of fat. And then each one of these is times 4 capital C calories per gram for carbs and for protein. And so calculated calories per serving. Now I'm just going to add all those up, right? Based on the numbers I just looked at, I should have a total of 232 calories per serving. Now the label told me 230. Why? That's because of labeling laws. So you should know a couple of things about labeling laws in America, at least. One of those rules says that you're allowed to round these starting numbers. So this fat number can be rounded to the half of a gram. And so sometimes when you see something that says it's fat-free, it'll say 0 there. It could be as high as 0.49 grams per serving, and it would round down to 0. Sometimes manufacturers tinker with their serving size to get that math right so that they can round down instead of having to round up. You'll see that a lot of times on cereals and sort of dry goods and stuff like that, and prepared foods. The other thing is that for calories, you're allowed to round to the 10. And so even though there's 232 calories per serving here, they're allowed to round down to 230. Is that fair? I don't know. I think the idea is that it makes it look more simplistic if you have, round numbers instead of 232 or 237 or whatever. But that's the reality of it. The other thing you should know is that that rounding thing goes for other sub-entries as well. So things like saturated fat, trans fat. It can be up to just under a half gram of that material per serving, and they're allowed to round down. So for trans fat in particular, which we know to be particularly dangerous for health, has a lot of cardiovascular effects and other things, you want to watch out for the word hydrogenated. If you see the word hydrogenated in the ingredient list, there is trans fat in that material. And so even though the number says 0, it probably isn't actually 0. It's probably point something between 0 and 0.5. So try to avoid that. It's going to give you an overall healthier experience based on where the science is right now. But that's a discussion for another day that I would love to have. If you're interested, shoot me an email. But that's your lab for this week. So you've got the 3 different ways to look at thermodynamics. And if you have questions, please get in touch with me, let me know, and I'd be happy to work through things with you. So do take a look at the PDF. I always say this. I want to make sure I say it again. Do take a look at the PDF. It walks you through all of this stuff. The calculations are kind of walked through just like I did it. So stepped through all of this kind of stuff. So take a look at the PDF. Start there. Take a look at the other things in your textbook, the worksheets posted to class, things like that, and shoot me an email if I can help. So with that, have a great day, and I will talk to you all next time. Take care.